with the keynote speech and panels. Conclude our conference with a dinner and tour of the Bosphorus. We hope to see you aboard. Now, to introduce our first keynote of the day, I invite Senior Expert of Ericsson, dear Dr. Erik Dahlman.
So, thank you very much, and thank you very much, Professor Arslan, for inviting me to this. It's unfortunate. Unfortunately, I will not be able to have a look at Istanbul this time. I hope I will come back again later. And I must agree with what I heard yesterday, that I think this event has been a truly, seems to be truly amazing event, and I actually believe that, your country can be very proud of this. So, what I have here is 6G, why, how, and when. Somewhat difficult questions, I guess, especially the first one. Why? How is a little bit easier, and when is very easy, let me know. But I think there are people asking kind of why do we do this? And maybe even more fundamental question, what is 6G? It seems like we're doing this we make a new generation every 10 years by some kind of regular cycle, like some law of nature. And we started with the kind of carryable phones, and then we came to handheld phones, and then we came to kind of first set of a little bit more cool phones with video capabilities, etc. And then, of course, came 4G with the smartphone revolution. And in 5G, we continue with smartphones, but we also at least hope to extend it into more kind of industrial applications, other things than smartphones. And a very simple way to say this is 6G is simply, the next major step in wireless connectivity that then hopefully bring new capabilities and enabling a lot of new services. An even easier way to say is simply that 6G is the wireless connectivity we will have in the 2030s. So that kind of creates the question, what do we need for 2030? And this is a little bit of a fluffy slide. I'm not so fond of these slides, but we typically have to show them because it gives a good impression. What do we see for the 2030s? We will, of course, the application demands will continue to increase, part of the digitalization, new services, new type of device types, need for higher data rates, lower latency, of course, partly driven also by a massive use of AI across the systems. But we also have this more kind of inclusion in the integrity in the sense that, wireless access is now starting to become more and more kind of necessity. You have to have wireless connectivity for your life, regardless of where you are. And we have to ensure that that's really possible, and that also will have kind of a very big impact on development all over the world. And then we, of course, have the sustainability and resilience aspect. We all know that we live in a world where we have to be much more energy efficient in general, and at least we believe that wireless connectivity can be a very important contributor to that. One simple thing is, of course, better wireless connectivity, less need for travel. I still hope we will be able to travel now and then because I like to go to other countries. But I think in general, we believe that wireless connectivity will be a very important tool to kind of create this much more energy efficient society. And then, once again, as wireless connectivity becomes more and more kind of vital part of society, of course, this aspect of trust and security becomes more and more important. We really have to ensure that our connectivity exists all the time, that they are secure, that they can't be kind of subject to cyber threats, and also ensuring that whoever we think we're talking to or communicating with is actually the one we are communicating with. And just kind of leads to some examples, what we see. On one hand, this kind of aspect of increasing demands from applications. We see, of course, a lot of mixed reality services, what in ITU goes under immersive communication, really the kind of services that push the boundaries of the capabilities in terms of data rates, in terms of latency, etc. Next, then we have this more like coming to this kind of inclusion. Is that we really see that we have need a truly global internet. I mean, you should be able to have connectivity wherever you are in the world. Sometimes I see it kind of connectivity needs to be in some sense as ubiquitous as air. If you go outside of a building, wherever you are, you expect there's air there in the future. You should be able to rely on wherever you are in the world you have connectivity. Smart transport is one of these aspects where we really see how kind of we can help or wireless connectivity can provide one of the tools to really enhance energy efficiency or sustainability in the world. And then finally we have this kind of resilient connectivity, as wireless connectivity will be a kind of a critical part of society in terms of providing kind of disaster relief and things like that, and I think that's also a very important thing. Now going to kind of a little bit more technical thing. I mean, so that we have 6G, and now everyone accepts that 6G, or no, not that's incorrectly. I mean, there is kind of quite a common view that 6G implies that we will have a new 6G radio access technology, kind of different from 5G. This is not completely kind of agreed on or something you don't discuss, because there are clearly many operators that ask, why do we need a new 6G radio access technology? Why can't we just continue with what we have? Why can't we just evolve 5G? Can't we do the same thing there? And hidden in that is, of course, then a feeling that a new radio access technology, some of them haven't even started to deploy 5G yet, and now they have a new technology called 6G, and that will be, once again, a lot of cost. But that, of course, raises the question, when is something new? Why do we call it new? And it's not so easy to say when is something in evolution of what we have, or when it's something new. And I would say that the simplest way to say if it's new is that we will have a new set of radio access specifications in 3GPP. And that has a benefit in itself. I mean, because we continuously evolve the standard specifications in 3GPP. I mean, we become like a first release of release 8 of 4G, and then we have release 9, 10, etc., and for the same for 5G, we have release 15, and come release 16, 17, 18, and they add a lot of features in that evolution. But experience tells us a lot of those features are in practice never implemented. But they are actually then implemented in the next release, in the next generation. So I mean, we added a lot of things in later releases of 4G, but they were never implemented in 4G. But then we came for 5G, they were part of the first release of 5G. So there is, once we make a kind of new set of specifications, new generation, we have like a better opportunity to really efficiently add these new features, whatever they are. It also has another benefit that typically you can never remove things from a specification. But when we create a new generation, we are actually able to kind of take away things that turn out that they were not so useful. And in that way, of course, we can reduce the complexity and the cost of the system. This being said, 6G will be very much based on 5G. It will not be kind of something that looks completely different. We will, now I'm somewhat speculating, but this is definitely our best guess at this stage. But of course, nothing is decided yet, but everything speaks of we will keep kind of the same basic physical layer as we have for 5G. We will keep the same kind of waveform, same kind of basic access mechanism, same numerology, same type of channel coding. For the simple reason, I mean, those things, they work fine. And we should not spend time and effort on solving problems that have already in practice been well solved. There are so many other things that we can improve, so we should focus on those. Then there are some other reasons actually why we will keep the waveform. I'll come back to that later. But I think this is important to understand. I mean, we do not expect 6G to look completely different from 5G. It will still be OFDM. It will be the same kind of numerology. And another very important thing, which I think is very, very important message to operators that kind of feel this kind of a little bit fear of, okay, now comes a new generation, a lot of cost. we have to ensure that we will have a very smooth migration from 5G to 6G. In principle, there is nothing that says that it should be more costly that go from 5G to 6G than it is to go from like one release of 5G into the next release of 5G. And I think that should really be our goal. It should be extremely smooth. So what are the capabilities we talk about? Of course, we want to always talk about new, cool type of capabilities, but in the end, I mean, some of the old-fashioned capabilities that has been there from 3G and even in 4G, in 2G times, will still be there. I mean, we will have need for high data rates. We will have need for higher network capacity. We will need for lower latency. We will have need for better coverage. In essence, I mean, we have to support even better mobile broadband than we do today. And we will also kind of go beyond mobile broadband, as we have already done for 5G. It's not only mobile broadband, it's also communication with machines, etc. Then there will be new capabilities, or partly new capabilities at least, to make a more efficient network operation. We talk, and I'll come back to that later, we talk a lot about spectrum sharing in the future, energy performance, more flexible deployments, possibility to have more available and resilient services, and also have kind of easier to introduce new type of services. And as I assume we all mentioned yesterday, I mean, they're also including this kind of beyond communication type of services, where perhaps, I mean, we already today have the positioning in our networks, which is kind of a service in our networks. That is not really about communication, although of course it relies so that we can communicate with the device. But then for 6G, there's also a lot of talk about this network sensing, which I assume was mentioned yesterday. And I will come back to it a little bit later. And just mention some of my favorite topics here that comes up. I mean, for example, take data rates. You will probably hear a lot about these kind of ridiculously high data rates for 6G. In the same time, we had ridiculously high data rates mentioned for 5G. The thing we typically call peak data rates. So typically, like in even ITU, they specify, we should have this peak data rate, and then we should have these kind of user experience or user experience data rate. And the peak data rates, they are just paper products, which you can hear from the number. I mean, if we have one set of user experience data rates, that means that the other ones are, of course, not user experienced, which makes them completely meaningless, because the only thing that means anything is what a user can experience. So even if we will still talk about these peak data rates for 6G, and we probably have these kind of ridiculous numbers of like 1 terabit or whatever, the only important thing is what we can achieve in reality. Those are the things we really need to improve. Focus on achievable data rates, and it could be not very high numbers, because in certain places today we have ridiculously low data rates. And if we can increase it, kind of, we have like going from 1 megabit to 10 or a few tens of megabits out on the really rural areas in Turkey. I mean, that could be very valuable. Probably much more valuable than supporting like 1 terabit per second at one very specific place somewhere in Istanbul. The same for latency. I mean, you will see these extremely ridiculously low latency numbers. Only relevant thing is the data to ensure that we can actually achieve lower latency. And maybe not even that is the most important thing, actually. It's the most important thing is that we should be able to support predictable low latency. So really we can guarantee a certain low latency, which once again is quite much more difficult problem, actually, than just be able to show that in theory we can have very low latency in certain situations. Network capacity. Everyone will talk about spectral efficiency, having more bits per hertz. We can't do much better than we do today. I mean, we are quite close to what's possible. We are also a little bit, I come back to that, running out of new spectrum. So at least I personally believe that we need, at some stage, to really densify our networks. Putting in more infrastructure, base stations closer to each other. Then one often get the answer, operators hate densification. I don't think that's really true. I think the operators hate the cost of densification. And I think the answer to that is not, okay, then we don't densify. I think the answer to that is, okay, let us then try to figure out how can we densify at a low cost. I think that's a much more constructive approach than to just say, okay, we will not densify. We will just run with what we have, and hopefully we can get more spectrum, which we will not get. Finally, about coverage, I think there are two aspects of this. I mean, one is that we are seeing that we really need truly global coverage, wherever you are, out super rural areas, out at sea, even in desert. In the long run, you should be able to have wireless coverage, which of course in some areas implies we have to extend our networks with some kind of satellite component. But it's also about this really true deep indoor coverage, where obviously satellite will not help. How will you be able to? I should feel absolutely confident that I will have coverage wherever I am, even deep inside building, even in cellars, etc. So, a set of kind of components that we believe are relevant for 6G. The first two ones I will talk more about later, this spectrum range, what are the spectrums that we use for 6G, and also this aspect of spectrum sharing. Waveform is of course important, but as I said, we expect no change from 5G. Maybe some extended numerology for some cases, but otherwise everything speaks in favor of we will continue with OFDM in the same way as 5G just inherited from 4G. There has been a lot of talk about this duplex flexibility, how you assign resources for downlink transmissions and uplink transmissions. A lot of talk have been on this full duplex as a very hot topic. I'm not 100% sure to what extent that is really the right way to go. Maybe the other one is more important, what we call downlink uplink separation. Today we typically operate uplink and downlink in the same frequency band. Or in TDD, of course, I say frequency. In FDD, they are typically next to each other. But we could actually gain quite a lot by going for let's put the downlink up on higher frequencies. Because on that downlink, we have a lot of power available at the base stations. But we need a lot of bandwidth for data rates. And have the uplink on lower frequencies, where we have less pass loss, because we have less power in the device. That would be a way of solve, or at least addressing this issue that we have in general, that we are typically coverage limited on the uplink. Enhanced MIMO may sound boring. We have talked about that for a long time. We had MIMO actually even in 3G, but it became important in 4G. It became super important in 5G. But I still believe that that's one of the tools we still have available to continue to improve things. More smarter antenna solutions, more antenna elements. Also this distributed MIMO, spread out the antennas. You're not only talking to one point, you're talking to multiple points at the same time. You're talking to the optimal set of points at a given time instant. Network energy performance, I'll come back to that as well. That's also very important. AI, I would probably be seen as insane exceptionally obsolete if I did not mention AI wherever I am in the world today. But it will have an important thing, and I will come back to that a little bit later. I already talked about the global coverage, and I will also mention a little bit more about this integrated sensing. And if I have time, I will talk a little bit about how I see these low power, wide area applications fit into the 6G. But in terms of spectrum, I think a difference today, I think we're getting more and more into a situation. It is not so much new spectrum available. So current assumption is really that the main spectrum that will be used for 6G will be the spectrum that is already today available and used for 5G, or maybe even 4G. And that, of course, that means, because we can't kick the 5G system out, that means that we need very efficient mechanisms for sharing spectrum on 5G and the future 6G network. And a key part of that is then that this is enabled by this, that we are actually, the waveforms will look the same. And I think that is one of the key important drivers, but the waveforms will look the same, because this is a necessary requirement that we have the spectrum sharing. And it's somewhat, I mean, we have the same thing already today with 5G and 4G. I mean, 5G has same waveform as 4G and compatible numerology, so we can really put 5G network on top of 4G network. It is not super efficient due to some characteristics actually of 4G, but it will be possible to make it much more efficient in terms of 5G to 6G spectrum sharing, because 5G is inherently more suitable for this. This is really not so much, it's not only a property of the new technology, it's really a property of the older technology, the legacy technology. 5G is allows for much more kind of spectrum sharing into the future. There will be new spectrum. Most, how to say, interesting is spectrum in the typically what we see is mainly 7 to 15 gigahertz range, what we call the centimeter wave spectrum. And that's sometimes seen as kind of, this is the new 5G, 6G spectrum, but that spectrum is not really available. And it will not be made available in the sense that we can kick legacy users out. And that means that if we're going to use that spectrum as new 6G spectrum, we really need means for coexist with incumbent users. And that could be satellites, that could be radio links, that could even be partly military applications. And we need to ensure then that the 6G system is such that it can really work in that way. Work when that spectrum is available, avoid interfering with the incumbent users. Then there is also, it was even more talk about for a few years ago, this sub-terahertz spectrum, going beyond the millimeter wave, going up beyond 100 gigahertz. That is, I mean, it is potentially useful for extreme data rates in limited environments or special situations. I mean, one thing they talked about, it could be fantastic for backhaul, wireless backhaul. But it is definitely very limited use in the most cellular applications. And honestly, today, we are not expecting this spectrum, support for this spectrum, to be part of the first 6G release. It may happen, but I mean, it sounds, if you listen also to other companies, it sounds more and more that there is a less interest in that, and most likely one will skip that for the first 6G release. Network energy performance is very important. I remember when we did, up until 4G, including 4G, we didn't really care about network energy performance. We who work with the standardization. We were very interested in device energy performance because the device had a battery, but we thought that, the network, you have 2 holes in the wall you can put your base station into, so you have whatever energy you need. Then came, of course, all these kind of sustainability discussions, but I would say came even more the fact that one started to realize that energy cost a lot of money for the operator. So suddenly energy performance became very important, and it's even becoming more and more important. And of course, it depends to a large extent on implementation. But it is also kind of property of the basic technology or standard, in the sense that if you have a good standard or technology standard, does not guarantee that you will get energy efficient networks, because you can do wrong error in the implementation. But if you have a bad standard, it doesn't help what you do in implementation. You will still have a bad energy consumption. So it is important that we do things right. And we made a major step in 5G with what we call this lean design, which essentially means that, as it turns out that actually a large part, the early networks, they essentially use more or less the same amount of energy, regardless of if you actually have some load in the network or not. I mean, it didn't matter if you transmitted any useful bits, because you transmit a lot of other stuff, system information and reference signals and synchronization signals, etc., all the time. So what we did in 5G really was that we minimized as much as possible this, what we call always-on transmissions. So that essentially, as much as possible, we should only transmit when we have useful user data to transmit. And that also meant that we get from a situation, as you can see here, from 4G, we had the energy performance was rather flat. It didn't really depend on the load until a situation where we still have quite high energy consumption when we are at high load. But that's in some sense fine, at least as a first step, because then we're at least doing something useful. But we were able to reduce the energy consumption quite a lot at low load. And what we see is that for 6G, we will continue with that. We will kind of further have this lean design, not only in time, but also in frequency and node domain, in essence saying that, okay, maybe we should only, certain frequencies should only be active when there's actually data to transmit. The entire frequency is only active then. Or even going one step further, some nodes are only actually working as data transmission nodes, which a little bit comes to the next bullet here. We decouple this kind of idle mode where base station keeps track of where devices are, and devices keeps track of what is the best base station right now when they are kind of in idle mode and not active devices. We decouple these two things so that we can have only a limited set of network nodes are these that keep track of all the idle devices. And a large set of their network nodes are only kind of transmitting user data. That of course means they can't be detected by an idle mode device. But that's fine, because the idle mode, there are other base stations that take care of that. We also need to have some kind of scalability, because what really drives energy consumption is often these kind of very extreme requirements. I mean, if you're going to support extremely high data rates, etc., that drives energy consumption. But those are very high data rates. They're only needed in certain areas. And we should ensure that that requirement at that area does not drive the energy consumption all over the network. Wireless and AI, as I said, you have to talk about AI. And I mean, as I see it, AI comes in, I actually like to call it machine learning, because sometimes I don't think they are very intelligent, because they have to look at like 1,000 rabbits to recognize a rabbit, while a 2-year child can recognize a rabbit after seeing a few rabbits. So they're not very intelligent, but they're learning quick. But it comes into two places. One is that, I mean, there will be a lot of AI functionality all over society. I mean, there are a lot of AI-boosted machines, and they need to communicate with each other. And we have to understand, how will that impact the requirements on networks? Will those kind of AI-based entities have new requirements on the network compared to what humans and other entities have today? So that's one part, I mean, in the sense that the fact that more and more AI in society will give us more requirements. But the other one that is, of course, more interesting for an engineer is the fact that, I mean, how can we utilize AI within our networks to boost the performance and the capabilities? So that really provides us not with new requirements, but really new solutions. So that is what kind of, both of these are very important for us, because we have to understand requirements and we have to understand how we can use AI for new solutions. And about this AI for wireless, I mean, how this has kind of using AI to improve our networks. Sometimes you got to feel that AI is kind of a magic tool. Whatever problem you have, a problem you can't solve it, then we say we solve it by AI. I don't think that's really true. To me, it's not really a magic. In some sense, simply speaking, it's just in some sense just non-linear signal processing with a lot of data. But I think my feeling and my gut feeling is really that it's really mainly beneficial for these kind of hard to model problems. I mean, problems where we today do not really rely on some solid model with corresponding theory, but where we rely more on intuition. I mean, in some situations, we have a good model of the problem, and we can actually derive the optimal solution. And if we can derive the optimal solution, I mean, AI cannot do better. But in many cases, we are really more relying on our gut feeling. And it's areas like resource management, we don't have any theory for that. At least we don't use any real theory for that. Mobility, we don't have any Shannon theory for mobility or for network planning. Those are areas where I believe AI could really play a very big role, because that's something that kind of is a lot of effort and a lot of cost. I tend to believe that are slightly less gains for the kind of basic physical layer functionality. I hope it's not only because I work with physical layer functionality and I kind of, I don't like new things, but I feel that in those areas we are quite close to what Shannon says, etc. And I mean, you can have a very smart thing, smart AI algorithm. It can't be better than Shannon, as long as the Shannon model is kind of correct. But then there are situations really where it's not of course, there are non-ideal situations, and then you can see some gains. I have just one example here. This is very simple. I mean, we have these demodulation reference signals in 5G that will have you send them you can send them on every second carrier. But it turns out, I mean, if you have some kind of AI-based joint channel estimation and detection, you can actually send them a much sparser, so you get kind of reduced overhead, and you can add more DMRs for more antennas, etc. So in this case, you can see quite of a big gain, but that's a very special case, and it's still in some sense a very small thing. I'm a little bit skeptic to these kind of things. We're going to have some kind of end-to-end AI, and AI will replace 3GPP standardization. I don't think that will happen for 6G. Finally, integrated communication sensing, also very much talked about. Sometimes I got the feeling that people see this as the main new things with 6G. I'm not sure about that, but I mean, in general, what is sensing? To me, sensing could be more things than this, but at least when we talk about ICAS, it's typically sensing is like determining the presence, location, and speed of passive objects. Could be a car, drone, or person, and passive means they are not kind of transmitting things. It's not a phone. So in some sense, it is very much related to positioning. The difference being that positioning is about determining the location of an active object. So in some sense, you can see in my picture here, I mean, we have like a drone. One way of detecting the position of that drone is if the drone was actually making a transmission that was received at base stations. But what we do with sensing instead is that we have another base station or some other node that is actually transmitting a signal that is reflecting on that device, on that drone. And then from that reflection, you can detect the position of the drone. And so that's kind of more, I mean, this could be the kind of normal, general sensing, regardless of kind of ICAS. But I mean, the thing with ICAS is really that we are reusing our net communication resources for the sensing. And it could be just reuse the infrastructure. It could also be used the spectrum, and we could kind of reuse the devices, which in some sense is part of the infrastructure. And it could also be even more kind of using the same waveform, etc. And as I see it, I mean, the main benefit with this is really that we can introduce sensing functionality at very low incremental cost. Because we have to admit, I mean, we don't know yet to what extent sensing will be a big success. So it's really unlikely that someone would build a completely new network just for sensing without knowing it will be a success. But if we can introduce it as part of our network we anyway deploy for communication, we can really introduce it at very low cost. It's in some sense similar to once a long time ago. We didn't really know if mobile broadband would be a big success. But we could introduce mobile broadband as part of a 3G network that we anyway deployed for speech. So in some sense, the business case for deploying the network was already there, and then we could start to introduce mobile broadband services essentially for free, because initially they just relied on spare capacity. So I think that's the same thing here. I mean, we have something we deploy for communication, and we can then start to introduce this kind of sensing functionality and see to what extent is it really kind of a big thing. And it can be used for two things. It can, of course, be used to enable new and enhanced services to the end user, but it can, of course, also be used as part of the network to improve the network performance. I think I will skip this IoT slide and go directly to my final slide about the easy question, the most easy question, the question that we already know the answer to, more or less, the when question. What is the timeline of 6G work in 3GPP and ITU, and when will we start to have things available to deploy? I mean, 3GPP has already started to look into 6G. looking into requirements for 6G. That's the thing we always need to do. We need to do determine requirements before we can actually start to develop technology. And we do that in some sense, I mean, with at least interaction with ITU, because ITU, of course, also do performance requirements for what they call IMT 2030, which is the same thing as 6G. But already next year, the plan is that 3D people will start a study item looking into the detailed technologies. And I mean, a study item, it sounds like just like studies, but I mean, a study item really makes all the fundamental decisions. What are the waveforms? What are the basic structures, etc. And then in release 21, which is like starting early 2027, start the actual detailed standardization. And then we really talk about putting the bits into place, I mean the small stuff. And everything then in order to have first being able to have something to submit to ITU as part of the proposed for IMT 2030, but also to ensure that we really have final specification available in 2028, so that we can start to do the development and have essential products, networks, and devices available in 2030. And I mean, I think the key message here is really that 6G is, I mean, actual work on standardizing 6G is, okay, it hasn't yet started because it's still just discussing requirements, but it will start very soon. And it's really that kind of reminds what I told, I think it's Professor Arslan yesterday, that I think that if one really want to academic frontline research, quite soon, you will have to start to rename this conference the 7G conference, or at least the 6G evolution conference, because I mean, how the first release of 6G will look like, it will relatively soon be nailed down already. So I think that's an important thing to have in mind. I think that's very good. I mean, I think in general, I mean, typically I think that academia, universities, they should be further ahead. I mean, they should be leading us, not coming hand in hand with the industry. So I think that is the main message here as well. So hopefully I explained a little bit why we do 6G. I mean, it's kind of boosting primarily further boosting performance and capabilities of our networks. A little bit what it is. Honestly, it will be in many ways, at least on the lower layers, quite similar to 5G. But we're making new specifications. We will be able to refine a lot of things, and we will be able to add a lot of features, or have a lot of features that we may even have in 5G already. But they have been introduced in 5G at such late stage, so they will never be implemented in 5G. But in 6G, they will be there from the start. And about the timeline, 6G I mean, 3GPP has already started to work on it, and within a few years, we will have the final specifications ready. Thank you very much.
Okay, Erik, thank you very much. When I was working at Ericsson, of course I was in North Carolina, RTP, and Erik was in Stockholm, Sweden. He was known as the godfather of Ericsson. So I learned a lot actually from him when I was working, and that learning process continued even after I left Ericsson. As a matter of fact, you know, some of you are familiar with his books about 4G, 4.5G, 5G, maybe a new edition, 6G will come soon. Working on it, I guess. Huh? Anyways, and he has also some videos, YouTube videos actually, and some of them actually I watched them 10 times. Just maybe I missed something. You have to listen to him very carefully, because if you miss, sometimes the messages he doesn't emphasize, but there is a lot of messages in his talk, so you have to go back and then rewind and then listen to him again. Because I think in this 40 minutes, he delivered maybe like 50 messages, so you have to, and we are recording it maybe, you know, when you are over with this conference, you have to go back and then watch it again and again. And I already noticed some of those messages. Anyways, I know what you are going to ask, Salah. He's going to ask about waveform. I can guarantee.
Okay.
He's a waveform guy. So let's I mean, you can ask questions. I mean, like I said, you know, he has enormous knowledge about, you know, all the way from second generation. I don't know whether you were there in first G, but I know that he has been there since the second generation. He knows wireless in and out, everything. I mean, like, he's a very valuable resources. I invited him several times to these conferences. Every time there was something, but finally we made it. I mean, he is here, and let's, you know, if you have questions, Salah, go ahead.
Waveform.
I think so. I don't know.
Hello, Professor. Good morning, everyone. Thank you for the interesting presentation. It was really good, realistic, yet a little bit disappointing. Saying that 6G will not be different totally from 5G, will not be a new technology was a little bit disappointing. To emphasize that, I need to go back a little bit to 3G. The upgrade from 3G to 4G made an enormous impact on the technological industry, and the world became an information-based world due to this upgrade. We haven't seen this, unfortunately, from 4G to 5G, even though 5G came up with new application, but there was not much done on the technology itself. It was still based on OFDM. We just introduced numerologies. For those who knows what numerologies are, we just introduced interference, a new problem, and we tried to solve it. So saying that 6G is going to be based on this problem itself was a little bit disappointing for me. The question is, what is the reason for this? Is it because that you believe it really works better, or it is because of the lack of the research done by the companies, or it is due to cost? My second question is, if there will be any breakthrough technology in 6G, what do you think it is going to be? Thank you.
Thank you for the question. I think what you're asking is very relevant questions. I think in some sense, I feel a problem we have is that we have this kind of periodicity, that as people start to, there will come 6G within 10 years from after 5G. And then we are in a situation we have not seen any major breakthrough. We could, of course, say, let's wait until we get a major breakthrough with 6G. But that will not happen. I mean, I can assure you that. I mean, then someone else, some other organization will do 6G. So I think that, I mean, I think that's the main reason. Currently, as I said, two things. I mean, one thing, we don't see any, like, example, new waveform that is kind of dramatically better than what we have. Two, and that comes this, we will not have sufficient new spectrum. We have to, the other one that's more practical, we have to operate in the same spectrum as 5G. And there's no way we can operate in the same spectrum as 5G unless we have something which is compatible with the 5G waveform. I mean, the alternative would be say, we don't operate in the same spectrum as 5G, but then we don't have any spectrum, and then we can have any real new spectrum, and then we can have essentially as fantastic waveforms we have if we don't have any spectrum to run it in. So I think that's a problem. Now, does that mean I think we will run OFDM forever in 7G or 8G or 9G? Probably not. But I also think, as I said, I think there are so many other areas, because there will be a lot of new things, and so many other areas that we will also improve. So it's not so that we will not get any improvement. I mean, we are targeting quite substantial improvements as we go to 6G. It's just that that's not depending on problem on the waveform, but probably more on scheduling means, control channel structures, etc. So one shouldn't see it as a very small step. Then one can ask, if it's not a gigantic step, why do we do it? I think that should one always weigh against what is the cost. And I think, I mean, as I said, in general, our aim is that there's a step from 5G into 6G should be extremely smooth. it should be as smooth as if you evolved in some sense, because I mean that's also what we hear from operators. Most operators, they don't want to do anything new whatsoever. They want to just go, and I shouldn't say most operators. I say there are operators, especially in Europe, that are quite pessimistic, and they in general question, why should we do anything? Why don't we just kind of continue to evolve? And then our answer is that by doing something that we kind of speaking new radio access technology, but it's that kind of very well adapted to how 5G look like, you can get something in essence that is cheaper and better than just continue with 5G evolution. I think that's the thing. Yeah. But I think you're very valid question. I mean, and of course, if someone come up with something that was brilliant, of course, we had to kind of change this. I mean, if there's some new waveform coming up that is way better, or some channel coding scheme that is way better than polar codes, or something like that. Of course, I mean, we are not saying, we are not stubborn on not doing anything. It's just that and it's not only waveform, as I say, today we haven't seen anything that is substantially better than current LDPC and polar codes, for example.
Erik, I have a question. Based on your presentation, I think 6G has already started, at least in terms of specifications. And there is this trend of every 10 years we have a new standard. Now, if we are not going to have a new radio, significantly better new radio, I mean, why can't we wait a little bit more for this standard, at least for 6G, until we have something significant? I mean, like, we can improve 5G for some more time. I mean, what is your take on this? And why do we have to really do 6G and rush on it?
Very good question. And I'm going to admit, for quite a long time, was asking the same question. Why can't we just do evolution and wait until we get something new? Then I realized that for completely non-technical reasons, we need to do 6G, in the sense that if 3GPP does not do 6G, someone else will do 6G, and that would be a really big disaster, because I mean, people expect it. Then I said, just comment a bit, but every generation is kind of should be a new big step. I would actually say that we have done the biggest step we've done, except perhaps for GSM, that's probably even bigger step. At least what I've been working with is not really going from 3G to LTE. The biggest step was when we went from the first release of LTE, of 3G, into what we call HSPA. That was a much bigger step. That was the same waveform as we have for kind of the earliest first release of 3G, but that was a completely new way of transmitting things. All this kind of shared channel, fast scheduling, link adaptation, and honestly, LTE was very much based on the same thing. We just changed the waveform. So one shouldn't say, it's not so that always one just takes the big step, the generational shift. Once again, I think the biggest step technology-wise we've taken on the radio access was actually when going from what we call release 99 into the release 5, which was HSPA.
You mentioned, speaking of messages, you gave me a message saying that if 3GPP doesn't come up with 6G, somebody else will. Who is somebody else? Like Wi-Fi standards?
Wi-Fi or some company of its own that come up with some kind of proprietary technology? I think it's life has told us that so at least I have kind of changed my view, because I was somewhat skeptic at the beginning when we started to work on 6G. I mean, it's really the time. I mean, doesn't some of these operators say, why do a new generation? Why don't we just evolve? We can do equally well. But it's also this other thing that, I mean, we can, in paper, a lot of things we have in the new generation, we can have on the evolution of the previous generation, and we typically have. But they are quite often, we only have them on paper, the previous generation. I mean, we had MIMO in 3G, but no one built it, and then we got MIMO in 4G. And we actually have this kind of lean transmission in 4G, but no one ever built it, so we got it in 5G. Sometimes people say that I'm a little bit thinking about LTE now. I mean, the only kind of thing that was really introduced and used in 4G after the first release was carrier aggregation. That we used. But we have enormous amount of other things in the LTE standard that is on the standard, but did not really become into technology until 5G.
Okay.
It is a pleasure to see you here. We are still learning, as Mr. Aslan told. My question is about the architectural point of view. Will there be an 6G NSA, like when we switch from 4G to 5G, we first build the 5G NSA and then we switch to, we are planning to switch 5G SA. What about 6G?
I am not an expert on architecture issues, but I believe that from when we went to 5G, we had this NSA, and then we have this SA. And I would say that our thing is a little bit that the NSA, it came a little bit unfortunate. It came because we were in a little bit too much hurry, because some operators were thinking about they were running ahead and doing something proprietary otherwise. Our aim today is that we should only have standalone 6G. We should not rely on 5G for 6G operation, because it's we got into the kind of NSA for 5G introduction, but that also meant that there was a lot of things that we have in 5G standard we couldn't really use in the 5G networks. So in general, we want to avoid the NSA approach and go for the standalone approach for 6G.
Thank you. It's good to hear it. May I ask another question? It's about AI and energy efficiency. In every new G, we are talking about a better energy efficient technology, but when we try to implement the AI into a communication technology, AI is not an energy efficient technology now. How can we say the new G will be both include AI and energy efficiency?
Good question. As I said, I mean, clearly, I mean, AI can do fantastic things. I mean, completely magical things. But as I said, I mean, I am not that completely, how to say, sold into this AI all the way on the physical layer. But I guess when it comes to energy consumption, a little bit depends on where you do the training, or if you do the training online in the network, or if you just kind of have the model and run the model actually in the network afterwards, because I guess that's the training is really what, at least often, really what costs. And I'd also say, I mean, using AI in our business kind of means kind of a lot of different things. I mean, one thing, we can use AI. Sometimes you see someone say, oh, I come up with a new waveform using AI. But that's really, they have to be running an AI algorithm in their lab to develop a waveform, and then they put the waveform in, like in the standard. I mean, we could have done that earlier, but then we call it kind of, we call it computer search instead. That's one way of doing it. The second way is that kind of we putting AI into our receiver, for example. Still, almost just implementation. It's very little impact on the network. And then we have the really fancy things when we have kind of AI running distributed models, running both on the network and the device side. And those are the ones that start to become very complicated, because then we start to almost kind of mandate what kind of algorithm you should have in your receiver, for example. That's not really something we typically do. And that, I think you can see that when you looked into AI for Phi in 3D, for NR, that they had the kind of three different areas. They had like AI for beam management, they had AI for positioning enhancement, and they had AI for this kind of channel state reporting. And the two first was really kind of one-sided models. And those were easy to specify, because you don't really need to specify very much. You only need to specify maybe some reporting for to get the data. But the third one, the CSI reporting, was kind of much more difficult, because that's really made an assumption. You have to have a certain model that was running on both sides. And that's very difficult. But I mean, in the terms, I'm a little bit deviated from the subject. I mean, in terms of energy consumption, of course. I mean, especially if people claim, we can save energy by a more energy efficient waveform by means of AI. We have a problem if the AI algorithm itself wastes a lot of energy. But I guess I hope the people on NVIDIA and other companies are kind of working hard on that energy consumption as well.
Thank you.
Quickly, and then we'll go to that. I think there are lots of questions.
Okay. I will be here afterwards if you have questions.
So let's take a few more, because we have next speaker, and then maybe like we can have, during the break, you can ask your questions. Go ahead, Ahmed, quickly.
Hello, sir. It was a really great presentation, a very realistic one. And I consider the use cases you have here is definitely can be achieved with IFTM multi-numerology kind of system, but there are also a lot of critical scenarios and many problems related to waveform design in the literature, which a lot of researchers, me included, are trying to answer to these questions. Now, let's consider that we heard your expectation about IFTM multi-numerology is going to be the way forward for 6G, but I also wonder, there are some problems that IFTM multi-numerology that there needs to be fixed, and which of these problems that you expect that are also going to be in the 6G, in the scheme that you're presenting us, and which of these problems you also expect would be solved using IFTM multi-numerology waveform, again, in 6G standardization procedure?
I guess the most well-known kind of problem with OFDM is, of course, the power efficiency of it. And that, when I say actually OFDM here, I mean, I should have made a comment. If we would go up into the really high frequency bands, where we do not have any kind of reason to keep OFDM because we have to be compatible with 5G because there we will not have spectrum sharing up there. There I should say, there we probably would not have OFDM. There we would have some kind of single carrier-like waveform, but then we're going to say, okay, that's what we have all today in the uplink. We call it DFT spread OFDM, which is of course one type of OFDM. And so most likely we will have that, and most likely we would like to have that even on the downlink then. So I should have, I was a little bit colored by the fact that sub-terahertz is a little bit less kind of, how to say, hot today. But on that frequency, that's one. Other problems, I know that there are some companies that are promoting technologies that they claim are much easier to do channel estimation of. Kind of where you do, for example, where you kind of do the signaling not in the time frequency domain, but in the delay Doppler domain. I'm not sure that that's true. We have actually investigated that specific technology quite a lot, and we haven't really been convinced about that. One reason is actually that one thing is where you have your the information symbols, whether you can do channel estimation still in another domain anyway. But that's one thing. Then I could even also, of course, say that at least as that waveform is typically described, that is also a kind of OFDM, because it could be seen as some kind of, even the generalization of DFT spread OFDM when you do in 2 dimensions. So, I mean, that could come in, but I mean, right now on that specific one, I guess you know what I mean. We haven't yet been convinced that is those benefits, but we're still looking into that. Otherwise, I don't think we have seen any specific things with OFDM at this stage, but those are the 2 things being brought up, and the main thing I see is still the energy efficiency, which means, of course, that we will probably keep the DFT spread OFDM for the uplink at least.
Okay, well, I think we need to move to the next speaker because of the time. Otherwise, we are going to have to shift the whole, timeline. But Erik will be here during the break, and I myself, have a lot of questions. But let's thank Erik and
thanks to all of you, and once again, thanks you very much to you and for inviting me here.
No
it was
a
big pleasure. Thank you.
It's a pleasure to have you here, Erik. And we have a gift for you.
Yeah. We would like to thank to the dear Dr. Erik Dahlman for his inspiring speech. Now we invite Professor Dr. Hüseyin Aslan to the stage to present his gift. Thank you.
Let me introduce the next speaker for the time, saving some time. Well, Erik was the godfather of Ericsson, but we have another godfather of Scotland, Glasgow University, and he is a very dear and near friend of mine, and he has been working on wireless communication quite some time. He's also the Dean of Engineering College there in Scotland. I visited the University of Glasgow. It's a beautiful university, wonderful university. So thank you, Muhammed, for being here. Please.
Thank you very much, Hussein, and thank you very much for inviting me and giving me this opportunity as well. And I'm really grateful for your insightful arrangement of the talks, because I would thank Erik now, because he has set the stage very well for my talk. And he said it very well, that we should stop wasting time on problems that have been solved or where there are incremental gains. And we have to also start focusing on larger problems in next generation of wireless communication. And one of that larger problem is this time with 6G, we should not miss our blind sight and try to have, again in Erik's words, inclusivity and integration, right? So that's the focus of my talk, exploring the boundaries of 6G, how some of the lessons learned from the Arctic to the Andes could help billions get online in next generation of wireless technology. So this is all based on a paper from Proceedings of the IEEE, where I have to acknowledge my co-authors on this paper as well, whose wonderful work has been put together to identify some of the technical challenges and how we have solved them and put them in practice in different regions of the world. I will introduce the problem and share with you the state of global connectivity, which is not very promising, and the challenges that limit this connectivity for all vision. And then we will have some brief encounter with communications for hard to reach areas and communications for extreme conditions, how these two things can be achieved. And I will present to you some case studies which look at the deployment of these networks in certain areas and what lessons we have learned from that will be part of the conclusions. So, the state of the matters is not very good. 50% of the world is still unconnected. So this is billions of people, right? And everyone knows that digital divide is the mother of all other divides, like healthcare divide, education divide, other opportunities like employment and so on and so forth, all follow from the divide nowadays, because most of the economies as well as most of the social life is dependent on digital connectivity. So there are technical challenges in addition to governmental challenges and policy related challenges which stop us from bridging this divide. So some of those challenges, if we start with the political ones, there is the question of political will, the regulations that different governments make in order to include the rural communities in the fold of connectivity. The spectrum, and this morning Erik was talking about the spectrum as well, how we enable and ensure the policy by different governments of use it or lose it, or at least use it or share it type of a spectrum policy, which will enable rural connectivity. Then economic challenges include the capital expenditure because of the cost of the hardware as well as the cost of deploying it, procuring the sites and so on, and the return of investment challenge as well, because the rural communities sometimes cannot afford it, or the number of people in those areas per unit area is much lower. And finally, the purchase power of these people is not as well as the urban communities or richer nations. So in terms of social challenges, some of the needs of people in different global south and other regions are different, and their behavioral trends are different. Some people or some nations or some societies don't see digital connectivity with the same lens as we see in the global north or developed nations. So technological challenges are the most interesting one for us as engineers, and we have to identify how rural communities can be connected, and as in my predecessor's presentation as well, some of the solutions that we found in 3G and 4G have to be retained because they are the best suitable to serve rural and large areas. So in addition to hard to reach areas and this connectivity, I will also in this presentation show you some of the results, how we continue to communicate in extreme conditions, like very cold environment, sub-zero temperatures, as well as in foggy or dusty environments as well. And this requires new path loss models and new studies and new areas of research as well. Not designing new physical layer, but understanding how to communicate in those new environments. So two terminologies that we use very frequently in the paper as well, and I might touch upon them, it's important to introduce them clearly. One of them is hard to reach areas. So rural areas, islands, because it's difficult to connect them with a backhaul, tunnels, underground sites, sparsely populated regions, Arctic regions. So these are all hard to reach areas from wireless connectivity perspective. At the same time, then there are areas which may or may not be hard to reach, but the conditions there are extreme. For example, deep underwater, space, extreme temperatures, severe weather, and this could be sometimes because of disasters, and sometimes this could be a permanent feature. So let's start with connectivity in hard to reach areas. So I have already mentioned the digital divide, its economic impact, but it also has an economic potential as well if we are able to connect these hard to reach areas and reach those billions who are left in these hard to reach areas, because it can help in job creation, remote work opportunities, and their improved productivity with digital connectivity. It will produce growth in sectors like agriculture, fishing, logistics, mining, and so on, and enable local enterprises, people coming up with their own new businesses which require digital connectivity to reach global markets. So challenges start with providing power and energy to these hard to reach areas. And one of the very important feature there is, how do we measure the success? And one of the questions previously asked was, okay, we will be introducing new technologies, they will consume energy of their own. Would it still benefit in reducing the energy consumption of the future networks or not? So the answer is in the effort to have net zero technologies. So you can invest more, you can consume more energy, but if it can save more than what you consume, you are still with a positive solution. So there are many other challenges in these hard to reach areas. For example, the supply of these energy lines. Sometimes you're off grid, you don't have the grid supplies there. So you have to rely on renewable energy solutions and modern battery technologies to save energy for the gray days. So infrastructure barriers are one of the main challenge. One of the infrastructure barriers we have already seen in terms of power supply, but lack of the other basic infrastructure like roads and communication lines, for example, for backhauling, or roads for providing access to human resources for maintenance of these systems, are an infrastructure barrier. High cost of deployment and maintenance in these hard to reach areas, for example, highlands and islands in Scotland, also is a barrier. Then there are some geographical barriers, like for example, for islands, putting undersea optical fiber and those things sometimes are as expensive or more expensive than digging and putting in those. Difficult terrains in mountains or valleys could be a challenge as well. So all of these, they impact on the deployment of new infrastructure like base stations, and 5G, for example, promotes high density of large number of base stations, which is not suitable for these rural areas, including 6G as well. So now coming to human resource challenge as well, lack of skilled personnel who would live and spend their lives in those areas. So you may have to keep sending people to fix the problems in these networks from urban areas, so that continues to be a challenge. And difficulty in remote monitoring and repairing and upgrading. So some technologies, as we will discuss, like self-organized networking or zero-touch automation, could be the solutions to overcome these challenges. So one key area to reach these hard to reach areas in terms of digital connectivity is to motivate local communities to come forward and solve these technical issue with the help of the experts who can design zero touch systems. But these local communities have to collaborate with the providers of these services. Mobile network operator model has to change in order to provide connectivity in these hard to reach areas. So this requires the importance of the stakeholder involvement. For example, it could be government, local bodies. They have to all work together to provide the financial impetus to provide connectivity in these areas. And I will give you some examples in case studies where projects like 5G Rural First and 5G New Thinking, which were funded by Department of Science, Innovation and Technology or Department of Culture, Media and Sports in UK to promote connectivity to remote areas like Orkney Islands, which were 96th percentile in connectivity, available connectivity solutions at the bottom of that list. So collaborative efforts between NGOs and ISPs for rural Africa. I will show you one quick case study about that as well. So these are the example initiatives where local communities came together along with the technical solutions provided by engineers to connect these hard to reach areas. So the technologies that were used to bridge this digital divide include key technologies like satellite, especially the LEO satellites for low latency backhauling to provide this global coverage. LoRa networks, low power, long range communications for IoT type of applications. And here it's important, many people ask, do they fit with 6G paradigm? So 6G is not just about increasing speed, reducing latency, increasing the number of connected devices as traditional generations have been. 6G has to be more than that by including the inclusivity and integration as one of the objectives in 6G. So again, spectrum comes to the fold as well, and low-cost spectrum solutions like TV white spaces can also be exploited to connect these hard-to-reach areas. So these solutions have to be cost-effective because we have looked at the main challenge, which is average revenue per user in those areas. We have to keep it as low as possible. And in that light, self-organized and zero-touch technologies will reduce the requirement of having human resources doing these maintenance and fixing these problems, reducing the costs, the operational expenditure, and also energy efficiency. Again, when we are measuring this energy efficiency, we have to be quantitative to make this case because a lot of these technologies will consume energy of their own, right? So energy efficiency parameters like watt per unit area, if you're covering a very large rural area with slightly higher power, then you are still energy positive in achieving your objectives. Similarly, metrics like joule per bit, which measure energy for every unit of information being transferred, also help us quantify and compare more fairly different energy solutions that we have. So using an existing infrastructure and sharing of infrastructure by different mobile network operators is one other cost-effective solution for coverage as well. I've already mentioned LEO as a solution which provides constant coverage for remote regions, especially for their backhauling, and we have done this in highlands and islands in areas like Loch Ocean, where we are using commercial off-the-shelf LEO-based technologies to provide backhaul connectivity, and then we have put in our own ORAN radios and other radios to provide local connectivity. And in addition to LEO, high-altitude platforms, which have been under research for a long time, but maybe now is the time to now deploy them as well to solve this problem of connecting hard-to-reach areas as well. So briefly touching on communications for extreme conditions as well, before moving to some quick case studies as well. So environmental challenges like temperature, dust, humidity, and water in the system impact system performance, for example, due to floods and so on. Attenuation of signals in severe weather, such as heavy rainfall, fog, snow, that puts in a challenge of wireless communication, both for fixed wireless access as well as radio access in cellular infrastructure as well. And then some of this can come because of a natural disaster, like earthquakes or floods. And the first thing after these natural disasters that we need to perform very well is digital connectivity. So if that is not there, it produces a lot of hindrance in providing rescue and recovery services as well. So we need a zero-touch, pop-up or on-demand deployable system in order to provide this connectivity in environmental challenges like these. So technological resilience, so in terms of weatherproof hardware or ruggedized designs for space, for Arctic or very low temperatures, or for quantum cryogenic communication lines as well, we need these kind of new technological solution, which will rely on adaptive systems to maintain connection in these hard environments as well. So one of these solutions is slightly moving away from it's a type of a radio, free space optical communication, which provides high speed, high bandwidth connectivity without relying on cables, and can be used in disaster recovery. And its benefits include fast deployment, and it's less susceptible to interference, but it is impacted by weather conditions very severely. And NOMA as a technology to pack more users within the same spectrum without splitting either the spectrum or the time domain, again provides that high density coverage of more users with same radio access technologies as well. So looking at the resilience, it can be through use of backup systems as the redundant systems, use of mesh networks so that if one connection breaks because of the changing weather or because of the harsh environment, then other connection can still work. Of course, all of these have their downside as well, like introducing latency and so on. But these are the solutions which provide us redundant and resilient communication in these difficult environments as well. And finally, disaster recovery can be done with portable communication. Everyone has read in different research studies as well as papers about use of drones and other technologies to combat disaster scenario, and emergency communication systems to engage the first responders in case of any natural or human-made disaster. So it was talked about AI, artificial intelligence, or if you mildly put it, then machine learning techniques can be used in network management. Network management is a really, really huge problem with thousands of parameters to be optimized to make the network run as we desire it to run. And here, AI and machine learning can actually help us to optimize the use of the resources like bandwidth and reduce the latency and energy consumption of these networks. So the other important bit is predictive maintenance. So to predict the onset of degradation in performance, or to predict the onset of lack of service in certain region and be proactive in solving these problems as well. So again, in extreme conditions, as the weather changes, these kind of AI-driven networks can reduce the over-provisioning or over-engineering of these networks. Rather, the over-engineering only triggers in when the condition really becomes harsh and unavoidable. So now briefly touching some of these case studies with due acknowledgement to a lot of the other co-authors and colleagues, because I was not present in all of these regions. I can only take credit for Scotland-related case study, but the others are, for example, one was done in Arctic region where the main challenge was the harsh environmental condition, extreme cold, long periods of darkness and isolation, very difficult to reach for engineers to make any changes to the infrastructure. And the solution that was used was installation of off-grid base station, so no need for power lines there, and deployment of a specialized cold resistance hardware which could survive very, very low temperatures as well. And the outcome was we gained a lot of insights into management of a spectrum license in those new areas and the enhanced resilience of communication infrastructure in extreme conditions like very, very low temperature. Another case study in the same region where the main challenge that we tried to solve was the environment with significant communication barriers, including, for example, availability of appropriate sites, where we still needed reliable communication to ensure safety and operational efficiency of that network. So solution was to use high capacity wireless backhauling using mesh networking to bring in the redundancy and resilience into the system, and then high capacity adaptable and robust free space optical communication to again have a backup when the wireless communication stops working. And this brought us insights into mix of software defined radio and off the shelf solutions across a very broad spectrum, including visible light as well as the high frequencies. So this was weather resilient wireless network which was robust enough to maintain quality of service in adverse weather as well. One other case study where we addressed a challenge in South Africa where a lot of networking is available in urban areas, but even within that urban area there is an area which is deprived and has people with low affordability. And this digital divide is not like urban and rural divide, rather it's a digital divide because of economic reasons. And the solution was to provide low cost including free space optic, but also low cost or O-RAN based or software defined radio based solutions which are easily configurable, affordable, scalable to provide community networking. And that community networking could be used for health related provisioning in those areas as well. And power was provided by solar power, so reliability reduces, but at the same time the OPEX or operational expenditure also gets reduced as well. And then a lot of services were locally cached to provide quick access to this content. In Brazil, for example, we faced the challenge of high cost of a spectrum license, which was very discouraging in terms of return on investment for any mobile network operator, and high cost of initial equipment as well. And we exploited the local unlicensed technologies and TV white spaces within that region to explore the concepts of radio fiber as well as other deployments as well. So this provided us outcomes with prototypes of different 5G range network, which was a successful project, and use of intelligence and adaptive cognitive radio technologies, where radio can switch to different frequency bands depending on the availability after being deployed. In the interest of time, I'm skipping one of these, coming to Africa again, where there was a lack of medical practitioners and need for communication networks in order to provide connectivity for those medical practitioners. Again, these low-cost, self-organized systems were deployed there, which were robust broadband networks for vital medical applications with low cost of maintenance and repair. And then comes the highland and island solution, the Orkney Islands. So we are proud to say that Orkney Islands were one of the first 5G connected site in the UK, despite being the remotest location in the United Kingdom. And this was again enabled, it's a collection of around 70 islands with only 20 of them inhabited with around 22,000 people. So you can imagine that how cost inefficient it is to provide network connectivity for a commercial mobile network operator. So the local community in Orkney was interested, and it was energized through NGOs as well as local governments to come together to not only host these networks in local cost-driven models, but also to provide help and support to engineers who would maintain this system and are maintaining this system for now as well. So in the process, we have developed and published a rural connectivity toolkit which any other community can use to start the process and can get free help as well as advice from 5G rural first as well as 5G new thinking projects as well. Neutral hosting was a key here because cost of securing a site as well as deploying physical infrastructure either on existing radio towers or television broadcast towers is still very, very costly. So this brings me to a conclusion of some of these case studies. So what did we learn in nutshell from these case studies? As I said before, that 6G should not be missing its blind side. Many generations have come, and it's still the question of connecting the unconnected is still a question mark, right? So we need inclusion in digital connectivity, and everyone is convinced about that. There is enough data and statistics available that this digital connectivity is the mother of all other deprivations and divides that can be overcome by providing and bridging this connectivity divide. So focus areas are scalability, affordability, and resilience. And affordability comes from the start of how costly the infrastructure is that we will deploy. And then that is the CapEx, capital expenditure that we need. The availability of sites, how we can make it more efficient by site sharing, by neutral hosting and other solutions, the capital expenditure of deploying these new networks. But then the other important aspect is operational expenditure. And operational expenditure, two most important costs are the energy as well as the human resource costs. So energy costs can be brought down by, of course, machine learning based solutions which are capable of being always available rather than being always on. So we should have capability of switching off some of the subsystems when they are not in use. And then moving to human resources cost, zero-touch automation or self-organized networking can reduce the need of site visits and reduce the cost of running these infrastructure as well. So last but not least, as I said, encouraging the collaboration with local communities for not just future innovation, but hosting these networks, maintaining these networks, and then training local communities, maybe even school kids or senior school kids to be able to run and maintain and troubleshoot these networks when there is an emergency and a need to fix them with human input. That brings me to a close. I want to thank all of the co-authors of the paper and my colleagues at University of Glasgow, including Professor Abbasi, who is here and will give another talk tomorrow about some of the technical solutions, and other colleague, Dr. Popula, who is also a co-author and from University of Glasgow. He helped me in putting all this work together. Thank you very much.
Okay, now we are supposed to have a break by now, but I'll give just one question. But the other, if there is anybody else who wants to have a question, Ahmed, you have a question or? Okay, go ahead.
Indeed, especially for connecting the islands, right? So if the span is not too long, fixed wireless access can be one good solution. And the unreliability of fixed wireless access from the point of view of weather and other conditions can be overcome by having resilience in the network by different backup systems or using a mesh of fixed wireless access connectivity as well. And this is being used in highlands and islands.
Okay, so you can also ask a question, but the others who have questions, they can come here during the break, and then
Yes,
they
I
can
will stay.
directly interact and take a picture with them. This is a good opportunity, actually. Okay. Microphone da orada.
Thank you for such an interesting talk. I'm actually curious about deep indoor communications. I'm talking about tunnels or crowd buildings.
Yeah.
When we consider the frequency bands, centimeter wave or sub-terahertz bands provided for 6G, the attenuation of the electromagnetic waves will be at a horrible level. And when we consider these facts with the power restriction issues, is there any methodology to overcome this issue in the minds of academicians or the companies?
Yeah. So two very, very quick ones. One is one-size-fits-all approach should not be followed. So same frequency is not suitable to cover any type of region, right? So we have to use appropriate solutions for the challenge that we are posed. So the other important bit is for any indoor scenarios or very deep underground scenarios, sometimes we have to rely on help of wired connectivity as well. So taking the wireless signals from outdoor to somewhere as an access point indoor and then cover that region using that access point.
Okay. Thanks a lot.
All right, thank you. So 10:45, we are going to start the panel. We have about 20 minutes. So there is a radio fest. There are like demos of students. You can take a look at those. If there is anybody who has questions, please come here. And we have a gift for you as well. So we're going to do a lot of things in parallel.